So my name is Aaron Struck. I'm a neurologist at the University of Wisconsin, where I'm the director of neurophysiology and epilepsy. And today we're going to talk about the 2 Helps to Be score. This is a tool that helps in seizure risk prediction in hospitalized patients. I developed this in collaboration with 2 computer scientists, Dr. Ruden and Dr. Dunn from Duke and Harvard, respectively, and another neurologist, Dr. Westover, that heads the continuous EEG critical care monitoring at Massachusetts General Hospital, Harvard Medical School. So at my core, I'm a clinician, I'm a neurologist, and to ground this project, I'm going to give a hypothetical patient situation, something where we use this algorithm. So this here is a blood vessel that feeds the brain. This is the internal carotid artery. And there's this little bulbous appendage here that the arrow is pointing to. This is a weakness in the blood vessel wall. So this is called a cerebral aneurysm. And given enough time, the wall becomes weaker and it spontaneously ruptures. When this happens, the patient develops an intense, severe headache, alteration of consciousness, can even become comatose. Obviously, you go to the emergency department very rapidly after that, and one of the first things that they'll do when you're in the emergency department is obtain a head CT, so it's just a scan of the brain. And you see all this white fluid around the brain proper. That's blood, and that should not be there. So this is a subarachnoid hemorrhage. So this is a common clinical scenario. This is something, Brandon and I see on a weekly basis. Now, it's a very severe injury, but actually a lot of the brain damage does not occur within the first couple of hours. It can actually accumulate over time over the next several days to weeks. So really what our goal is after the initial stabilization of the patient is to try and prevent this secondary brain injury. And something that we're beginning to recognize is one of the mediators, one of the causes of this secondary brain injury are seizures. Now, seizures, when they come to mind amongst lay people, they think about somebody falling to the ground and having generalized convulsions. These aren't the kind of seizures that we're talking about. Patients that have this severe of a brain injury, often they can't manifest these convulsions. So if you're standing at the patient's bedside, you cannot tell that they're actually having a seizure. They're just a bit obtunded. And they're relatively common. So about 20% of patients with these kinds of diseases will have seizures, but 80% don't. And because you can't tell at the bedside whether the patient is having them, the only way that you can tell is with an EEG. So an EEG is just a test. You put electrodes on somebody's brain and you measure the electrical activity of the brain. So that's the only way that you can detect these seizures. And as I said, why do we care about the seizures? This is what happens when you have a seizure, when your brain is injured like this. The demand for oxygen and blood flow increases, and at the same time it actually drops. So you get this mismatch between supply and demand, and the brain tissue infarcts and the injury extends. So the brain injury worsens. So it's clearly something that we want to try and capture and prevent. So what is the problem? So this is a EEG. So you need to have a continuous EEG on to be able to capture these seizures. But EEGs like this are quite expensive, and even more than just expense, the skill set to be able to interpret them is not very common, even amongst physicians at tertiary care hospitals. And even more limiting are the technologists and the equipment, so the people that actually perform the tests. There aren't many of them. The labor market's very tight. It's hard to train and get enough of them. So really what we need to do is optimize the resources that we have. And currently the way that it's being utilized is really suboptimal. People that don't need to be on monitoring are on too long, and people that are need to be monitored are missed. So to address this problem, a group of hospitals got together. We formed this consortium called the Critical Care EEG Monitoring Research Consortium. And over the course of several years, we put together a database of over 5,000 different patients. And from this group of 5,000 patients, we had an extensive list of over 70 different clinical and electrographic variables. And these variables, prospectively, we acquired them. They're all clinically meaningful and well understood to physicians who deal with this kind of care. So we have this big list of descriptive statistics, but we don't really know how to move from that list to figure out who's really at risk for seizures and how can we use that to change our patient care. So this is just a brief sampling of a bunch of the different parameters that we looked at. Far too many for us to use on a single univariate way. What we really want is something that's pretty common in medicine. You have a few different factors, you assign them a different point level, you add them together and you use this to figure out who's at greatest risk for, whether it's stroke or diabetes or whatever it is. The way that these were traditionally developed is kind of ad hoc, like physicians felt, well, these ones seem to be the most important, or sometimes they would use, forms of logistic regression where they would round the coefficients, or even, more advanced regularized forms of logistic regression. We tried to do that with this data set, but we ran into a lot of problems. We were getting a lot of coefficients, or a lot of variables with intractable coefficients. It didn't really make a lot of sense clinically, so we were a bit stuck. So that's when I approached Dr. Westover, and he introduced me to Dr. Ruden and Dr. Dunn, and they'll explain how they solved this problem for us. So I'll let her describe that.
Thank you. So my lab is probably the only lab in the world whose sole focus is interpretable machine learning. And our goal is to design models that are not a black box. We want models that look like someone might have designed them, like a scoring system, which is what Dr. Shuck was looking for. This is a sparse linear model with integer coefficients. Now these kinds of models have a lot of, a strong precedent in medicine. They're very, traditional models. And they've been created by doctors for many different medical problems, but never seizure prediction. So I'm going to put up a model that is not a machine learning model. It's actually a model designed by a team of doctors, and it's for a totally different area of medicine, but it's probably the most widely used predictive model in medicine. And this is it. It's called the CHADS-2 score. So the CHADS-2 score takes the patient's age and their medical history and computes a score from it, which translates into a risk of stroke in the following year. Now, CHADS-2 was created by a team of doctors, not from data. It was created from experience, and it is not a machine learning model. So we want to create a model that looks like this and as interpretable as this, but we want it to be as accurate as our best black box models. Okay, now there is no prior scoring system for ICU seizure risk. So if we had taken the data that the doctors gave us, so over 70 features, and tried to enumerate all possible scoring systems from them, then we would have been here till the end of the universe, and that wouldn't have been a good idea. So we decided to do something different, which is to take the training data and feed it into one of our new machine learning algorithms and have it spit out not a black box, but instead a model that's actually interpretable to people. And that model is called the 2 helps 2B score. Now, 2 helps 2B is small enough that I can actually put it on a PowerPoint slide and I can actually show it to you. So this is it, 2 helps 2B. And so it's 2 helps 2B is 2 HELPS and then 2 points for the B. So the doctors, just by knowing the model's name, they have the model memorized. Now, this model was not created by doctors. It was created by putting data into a machine learning algorithm. It's a full-blown machine learning model. It's not just a rule of thumb. It's actually as accurate as any black box model we could construct. My group is expert there. We have a lot of expertise in neural networks and boosted decision trees and so on. We also like the interpretability has a great advantage because doctors can decide themselves whether to trust it. They don't have to blindly trust it like a black box. Also, doctors can calibrate the score with information that's not in the database because there might be unusual circumstances that might cause a doctor to adjust how they want to care for the patient, and now they can calibrate their score. Also, the score can be explained to non-physicians so that it can be justified why someone will be put on or taken off EEG monitoring. Okay, so I want to talk to you about the machine learning algorithm that produced the 2 helps 2B score. Now, most machine learning algorithms do not produce interpretable models, but this one does. And it's called risk-calibrated super sparse linear integer models. Okay, so the optimization problem that RiskSlim solves looks like this. So it's minimize a negative log likelihood. So this term says make the model accurate. And then this model size term says keep the model small. And then there's a set of constraints that says make sure that the coefficients of the model are integers. Okay, so let me show you the math associated with that, which is right there. Now, this problem has never previously been formulated in an optimization framework, despite the fact that doctors design these models regularly. However, even if someone had put it into an optimization framework, they couldn't have solved it because it's a mixed integer nonlinear program whose feasible region is the integer lattice. So if you tried to send it into Nitro or one of the MinLP solvers, you'd be here forever. It wouldn't work. So I'm going to show you how we did it, which was to design our own cutting plane method. Now, in order to describe what we did, I need to first go over traditional cutting planes so that you can see the difference between what we did and the traditional version. So let's say that we were going to minimize a smooth convex objective whose values are known to be non-negative. Okay, so in traditional cutting planes, you would start somewhere, and then you'd compute the objective and the gradient and create a cutting plane. And then you would try to minimize the cutting plane surrogate to the objective. But in our case, the function is known to be non-negative. So we're going to choose this point right here. And then we'll repeat. And then eventually, the minimizer of the surrogate equals the function value. And that's when you know you've solved the optimization problem. Now, something goes wrong with this when creating models with integer coefficients. So let me show you where that happens. So if you're here in the computation, so you iteratively constructed this surrogate, that when you minimize it, you solve a linear program. So the solver would compute this, you'd solve it LP. But in the actual optimization problem that RiskSlim is trying to solve, that is not necessarily the answer that we want, because our feasible region is the integer lattice. This is RISC supersparse linear integer models. And so we might want a point that's actually over here. So in that case, what we would have had to solve is a MIP, a mixed integer program, which is much harder to solve than a linear program. And we would have had to solve it to optimality at every iteration. Otherwise, we would never know when we have solved our problem. And so what happens at every iteration, you're adding a cut. And so the MIPS that you have to solve get bigger and bigger and bigger and more infeasible by the second. And you have to solve them to optimality. And so after a while, no matter how small your data set is, after 200 cuts, you just can't solve the MIP, and the solver stalls. So let me show you an example of where that happens. So in this problem, after about 70 iterations, the solver just choked and took over 10,000 seconds, and then we had to just turn it off because there was just nothing we could do. And this isn't even a very large problem. And the optimality gap, which is supposed to go down to 0, it actually just stayed up at 100% and never went down at all. So we designed a new cutting plane method that does not stall. Okay, so with this new algorithm, at each iteration, instead of solving the MIP at every iteration, it actually solves the LP, the linear program, which is much easier to solve. And so it gives you that solution. Okay, so what does it do with that solution? Well, if it happened to land on an integer point, we can create a cut. If it didn't, then we would subdivide the space and handle each piece of the space separately. So we would branch. And then at the next iteration, we would solve the LP, landed here, create a cut, continued. Okay, and this seems to really solve the problem. Like, even after you run it for 10,000 iterations, the solver still finishes in under 100 seconds, and the optimality gap gracefully goes down to 0. So we have no more stalling. And one very nice thing about cutting planes is that they scale beautifully in the sample size. So even if you have 10 million patients, the time you spend on the solver is relatively constant because the solver never really sees the data. The solver sees the cutting planes. The cutting planes are created from the data, but that computation is linear in the amount of data and not exponential. And so that's why it works so nicely. Now, risk-SLIM and its predecessor SLIM have been applied to many different problems across medicine and also in criminal justice. And the paper that we're talking about today is actually published in a top neurology journal.
So I'm going to tell you a bit about how we've been using this to change our clinical practice. So the first thing we had to do to make sure we convince our other colleagues in medicine, and I direct the monitoring service for for critically ill patients at Mass General. But the first thing we had to do was to validate this on an independent set of data, make sure we didn't overfit. So over here, this is the calibration curve, and the original risk-SLIM data set, this 5,000 patients, the performance is shown with these blue dots. So this is what risk-SLIM predicts in terms of probability of seizures, and then the proportion of those patients with a given score who actually did have seizures. And you can see there's this beautiful calibration curve. We managed to get 5 centers to pool additional 2,000 cases not used in developing risk-SLIM. And you can see that those green points also have essentially the same performance. So it generalizes well to new data. The next thing we did was to make it practically implementable. We needed to know how much data do you need, how long do you have to observe a patient's brain activity to know what their risk-SLIM score really is, or what their 2 helps to be score is. And it turns out to be, thankfully, just about an hour. And so after that, we were able to say, all right, once we know what your score is, so after an hour of data, how long do we need to observe before we can make a decision about how long you need to be monitored? And so we came up with this prescription. So if your score in the first hour is 0, it turns out using survival analysis, so the score tells you what your starting probability is, and then we can watch if no seizures happen, that decays down to essentially 0 for people who have a score of 0. Actually it's already down to 0 by that point. If you have a score of 1 or 2, then the time to decay down to 0 risk is about 24 hours. And if you have a score of 3 or more, then we need to watch you for about 72 hours. And following this prescription, so the status quo before having this was everyone should be monitored for 24 to 48 or more hours, just kind of across the board. So following our 2 helps to be's prescription, we're able to reduce the average time monitored by about 64%, which is a cost savings of more than $1,000 per patient. Another way to look at this is that means we have our resources available to monitor almost 3 times more patients than we otherwise, than we normally would be. So now, when a patient comes in with an aneurysm and a subarachnoid hemorrhage, we can look at the EEG for about an hour, and I can quickly see, actually, and I think you'll be able to see here, this patient's brain activity has, so this is left, right, middle. The left side has these abnormal, discharges, these so-called periodic lateralized discharges, and I can just look at the 2 helps to be score. I know that this risk, the patient has a 3, which translates into a pretty high probability of seizures. I need to monitor them for 72 hours, and if they're not already on anti-seizure medicines, I will start them. So it gives a clear recommendation. Now, Dr. Struck has managed to implement this at University of Wisconsin, and in 2018 saved $2.6 million. Is our estimate, and at Mass General we saved about $3.5 million. It's being implemented at multiple other hospitals in the US and internationally, and we estimate that if all of our colleagues who do this kind of monitoring were to adopt it, they would help more than 26,000 patients who are currently being monitored, save about $54 million. Most importantly, though, we'd be able to help more people who are currently missing and save lives, quite literally, and save brains. So just to summarize, 2 helps to be is an interpretable machine learning model that predicts seizure risk in patients who are critically ill. It uses a new optimization method that Drs. Ruden and Ustun developed. So it can make predictions that are accurate about the risk, and it also is prescriptive in 2 senses. The optimization sense that's being used in the conference, but it also tells us literally what to do, whether to prescribe medicines or not, how long to monitor people, whether they need monitoring or not. And it does all this in a way that's very easy for physicians to understand. And as I mentioned, it saves money, but most importantly, it helps us to save lives. Thanks.